What I have here on the bench today is an Agilent 66312A dynamic measurement DC source. It is quite multiple, but what it really boils down to is a two-quadrant programmable DC power supply. So what is a two-quadrant power supply, you may ask? Well, typically a power supply is a single-quadrant device, meaning that it can deliver current while outputting a regulated positive voltage. So in the voltage current graph, we can represent a resistive load with a load line like this. So here is our voltage axis, and here is our current axis, I. So because we can only output current from the power supply, we can represent a resistive load with a load line like this, with the angle here representing the resistance. So while we change the output voltage, you can see that the output current changes accordingly. Of course, if you are limiting the current toward voltage, then the line gonna fold, depending on which of the variable you are limiting. But nevertheless, because of the power supply can only source current, so the current is always positive, the load line can only stay in the first quadrant. In a two-quadrant power supply, as the name suggests, it can not only output current, but can sink current while maintaining load regulation as well. This can be implemented using a circuit called a down programmer. One device we deal with all the time that exhibits similar behavior is a rechargeable battery, in which the terminal voltage stays fairly constant during charging and discharging cycles. Your typical power supply, though, can only source current, so if you tried connecting a power source with a voltage higher than the power supply's output voltage, although this is not recommended as it could easily damage your power supply depending on the construction. But when you do so, the output voltage will become unregulated and approach that of the external power source, which has a higher voltage. Anyway, back to the two-quadrant power supply here. So it can be used conveniently both as a power source and a sink, which also functions as a load. Now, of course, there are dedicated test equipment called source measure unit, or SMU, or SMU, that can operate in all four quadrants. So in addition to the two quadrants we talked about, an SMU can also output a negative voltage, like in a bipolar power supply, but can also source current from its negative rail, in addition to sinking current like a standard negative output power supply does. Now, of course, a source measure unit has much greater functionality than our dynamic measurement DC source here, but in terms of principle of operations, they are quite similar. So what I wanted to do next is taking a quick look at its operation here, particularly the current sinking capability, and then we will open it up and take a look inside. Now let me power on the power supply, and we will take a look. As you can hear that the fan started spinning up, and this fan, I believe, is thermally controlled. Although it's always on, it is currently at its lowest setting. As the power supply started dissipating more power, we will hear the fan spins up faster. And also the power supply fan is a little bit loud, and I suspect that's because this unit had been in service for quite some time before it was retired. You can also see that from the dim display here. These kind of VFDs are notoriously known for getting dimmer over time, especially when you use it extensively. But this is not my main concern right now, as we can still see the digit. Although it looks a little bit brighter in the camera than in real life, but it's still legible, so we'll leave it alone right now. And so let's set it up to output a 5-volt voltage. So let's do voltage, output 5 volts, enter, 5 volts, and enter. And you notice it's still displaying 0 because it's measuring the voltage at the terminal, and right now it's disconnected. So let's check the current, and I think the current setting is at 0.2 amps. So let's do a set it at 0.5 here. So 0.5 and enter. So now we set up our power supply to outputting 5 volts and 0.5 amps maximum. So let's turn it on. and we can turn the output on. So it's displaying 5 volts. Let's just double check voltage here. And for that, I'm using this meter to measure it. And as you can see, we are indeed outputting 5 volts. So now let's double check the current as well. So let me put this to 10 amps range. And let's short out the output. And yep, it's showing 0.5 amp. And you can see that the fan, you can hear actually the fan spin up a little bit more. See, now it just quiet down a little bit. So it is thermally controlled, as I mentioned earlier. So anyway, so right now this power supply is outputting a maximum of 0.5 amps. And by the way, as you can see here, notice the sign of the output current is positive. Okay. And to test its current sinking capability, I'm using a current source, and this one is HP 6181C. So here are the output leads from the current source, and right now I set the output current to be roughly 0.24, 0.25 amps. So let's take a look here. So if I'm shorting that, yep, I get 0.24 amps. And let's just take it voltage measurement as well here. So the voltage measurement from the current source right now is at roughly 11 volts. So this is just to make sure that it's higher than our DC power supply's voltage, so that we can test the reverse current sinking capability here. So now let me plug this current source into the output of the power supply here. And let's watch what that current reading reads, and also at the same time let's read what the voltage is. And as you can see, the output remains at 5 volts, but the current becomes minus 0.2324 amps. So clearly this power supply is currently sinking current instead of outputting current. And that's the operating in the second quadrant instead of the normal first quadrant. And also you notice that the fan is a little bit louder now because we are sinking additional power into the power supply via its internal down programmer here. And so that extra power dissipates into the heatsink and causing the fan to spin up faster. So now you can see that this power supply is indeed capable of outputting current and sinking current. So now we have seen the basic operation. I'm going to power it off, and we will open it up and take a look at what's inside. And one more thing before I open it up, and I just flipped this over and you can see the rear side. And here we have a GPIB port and also an RS-232 port. So this one can be controlled either via GPIB or a serial communication. So we might be able to try this a little bit later. Besides that, it also has some I/O port here, and you can use this to remotely monitor the power supply. And also, we do have a back output terminals for the voltage output and the sensing. And so by default, the sense is should be local. So let's see. Yep, so it was pressed in, so it was local, meaning that we're using the front binding post output. If you were to use the rear side, you need to put that to remote. So let's push it back to local. And so that's pretty much all it has on the back side here. And we should be able to remove these two screws and slide the case out. And I'm going to do that next. And I think we need to also remove these two screws as well. And I just managed to slide it out look at how dusty this whole unit is. I'm actually quite surprised. I haven't seen one this dirty for a long time, and you can see that this fluffs from the dust, environment dust, is all over the place here. And so I'm guessing that this unit was probably left in a pretty less environmentally controlled area, and it has been on 24/7, something like that, all the time. That's why it is so dusty inside. So I'm afraid I have to first do some cleaning before we can continue this video here, as I don't want to get everything all dusty here. And also it's you can't really see much with all the dust covering everything here. So I'm going to clean this unit up, and after that I will be back. And as you can see here, I spent quite some time. Actually, I had to take out all the boards because it is quite difficult to clean each individual board with everything in the case. But anyway, so I took it out and managed to clean everything as thoroughly as I can. Use this isopropyl alcohol and 99.9%. And you can get away with 91% alcohol, but just make sure that the board is thoroughly dried after you do so, because you don't want moisture to leave on the board, and later on it might cause some corrosion. And I did not take any video footage of while I was taking this whole thing apart, because it was very messy. Yeah. So the first thing I want to show you is this main board. And from this side, you can see that we have this precision resistor. Actually, this might be just a current shunt. Yes, it is a current shunt. It's a 0.25 ohm. And we can see that it has 4 leads, so this is clearly using the Kelvin sensing here. And then we have the bank of transistors mounted on this heatsink, which the fan is blowing through the heatsink to cool it down. And then we have this interesting looking capacitor here. Not sure why we need this type of capacitor, but presumably it's for stability and so forth. And when you look at the chips on here, the only things I see are pretty much the OP27 op-amps and a bunch of transistor arrays. So it's nothing special here. Now, so I assume that the actual regulation is happening on the other board, the riser board, which we can take a look later. But here you can see again, on this side, these are the capacitors from the filtering side. And these are, let's see, yep, so these are, is that a Nikon? Yeah, Nikon caps, so they are pretty good quality ones. Of course, we can't expect anything less from an HP power supply here. And I really like this hard power switch, which you can use this rod to push it in, and it's mounted towards the back. But so on this side, we also have some linear regulation going on here, and these are providing the rails needed by the remaining of the circuitry here. So again, on this main board, we only see a lot of the we can see a lot of the power devices, and in terms of the ICs here, I'm not seeing anything that is related to the voltage reference or things like that. So I bet those chips are on the other board. So now let's move on to the other board. Oh, by the way, I did manage to take the fan off and clean it a little bit, and I think it might be quieter after I reassembled it. I didn't have a fan of the same size, so I would right now just leave it alone, and if it gets worse later, I can always replace it. Also forgot to mention is, besides this shunt resistor for the 4-terminal Kelvin sensing resistor here, we also have a what looks to be a current transformer here. Presumably this one is for measuring the AC components of the current, because according to the user manual, you can also use this device to measure the AC components as well. So now let's move on to the other board, which this one is actually lying upside down on the main board, on top of the main board, and so you can see that we have a GPIB output and RS-232 output, and we have the RS-232 driver right here. And towards the center, we can see a DSP, digital signal processing chip. This chip basically handles all the processing of the power supply here. And then we have a Xilinx FPGA chip here. And this one would have a lot of the custom logic built in as well. Besides that, we have quite a few of these. I'm not sure if these are CPLDs or these are just ROM chips, but these are holding the specific logic and firmware here inside. And what else? We also have a, let's see, so now I can see that the chip here, and what I recognized is this MAX 5328. So I believe this is actually a 12-bit DAC. So this makes sense because the voltage output and current output programming resolution is a 12-bit. So I'm betting that this is what is controlling that for. And then we can actually see a little bit more because if you notice up here, so I'm not sure how well you can see it, but later on I might just include a picture here so you can see it better. But up here we have this looks like a TLC 5620. That's a 8-bit DAC. And we also have this analog device AD7524, which is another 8-bit DAC. And here we can see a AD677. This is a 16-bit ADC, and that makes sense because the readback accuracy is 16 bits in this power supply. And now if we look up here, we can see you can probably, I'm not sure if you can read, but this one is our voltage reference. It's an AD586, which is a 5-volt precision voltage reference. I think it has a 2 ppm stability, but not quite sure. I will try to find a data sheet and put it on. Now, of course, a lot of these chips are quite small and you can probably not see it very well, but I'm going to take some high resolution pictures and post it on my website. So if you are interested, you can always hop over and take a detailed look. So this is our digital board. And also we have some drivers for driving the GPIB and our RS-232 and also our digital I/O pins right here. So that's how this power supply is put together here. And I also took off the display board because this board is actually very dirty. So after I took it off, I noticed that the whole top side is covered with dust. So I cleaned it, as you can see, quite thoroughly. So hopefully this will actually make it a little bit brighter. And also the contacts for these buttons also were covered with dust. So that might cause some problems, long-term reliability of those push buttons on the front panel. And here, I believe, is the charge pump circuit, or it's actually a DC-DC converter circuit. Not sure, entirely sure, for powering the VFD. And this one would generate some higher voltage, maybe 60 to 100 volts, depending on what the specific VFD this is, and to power the VFD. And I forgot to mention is that I just printed out this block diagram for the main board, and as you can see here, we can see that we do have this output regulator, which is a bypass transistor here, which are mounted onto the main heatsink. And then we have the down programmer section right here, and of course we have our output crowbar circuitry. And so the transformer you see here, this is the current transformer that we mentioned a little bit earlier. And here you can also see we have some professional bodge here, and I don't think these are soldered on after the fact, but these are probably from the original manufacturing, and they must have decided that they need some resistors here, and they have no footprint, so they just flew it over the IC here. And towards right here, we have a couple of Cypress SRAM chip, which probably stores some of the configuration for the DSP or the Xilinx. I'm not entirely sure. Now that I've cleaned everything up and also have shown you each individual boards, let me put everything back together, and hopefully it still works. And I'm going to do this off camera because it's just going to be boring to see me putting everything together, and after I'm done, I will let you know. And as I'm in the process of putting it back, I just want to show you something that I forgot to mention, is that the power output is from these two wires. Notice that they connect directly to the front terminal, even though this has a 4-pin connector, but only the positive and negative. These two leads are connected, so which means that the voltage sensing rather, is not going to work that well for the front panel output because the sensing terminals are located all the way at the back. So the voltage drop when you're using the front terminal could be significant, depends on the current output you are using. And I just put everything back together, so let's power it up before I close the unit up. So just to want to make sure that it still works. And it still works. And the fan is, well, after I cleaned it, it's still a little bit loud, but as I mentioned earlier, I don't have a replacement fan, so we'll have to just live with that. Now let's take a look. Output on, and we can adjust the voltage, no problem at all. So at least we cleaned up the unit. So now let me put the cover back on, and we'll hook it up to the computer and see the RS-232 communication with this unit. As I mentioned earlier, you can either use a serial cable or a GPIB cable to communicate with this Agilent 66312A. Now, of course, we're going to try using a serial cable to communicate with this device. Now, the specific serial cable we used is called a null modem cable. Basically, has several signal pairs crossed over. So this is important because if you have a straight cable, it will not be able to communicate with this Agilent device. Now, the cable we use are both sides are the female connectors, so you can readily find these kind of cables online. Also, before we start a communication, we just need to set the interface to be using the serial port instead of the GPIP port, which came in as a default. So let's take a look at the address. It's address 0, and we will change it to so right now the interface is a GPIB, so let's change it to let's see, how do I change this? RS-232, and we should be able to enter, and that should do it. So let's take a look again. So let's power it off and see if it memorized the settings here. Yep, so it shows the baud rate at 9600. So now I believe the interface is indeed using, oops, we're not going to change the baud rate, we're going to change the, interface is RS-232. So we will use this to communicate with our PC shortly. So now on the screen here, you can see a serial terminal program, and this is a MO serial. You can pretty much use any serial program that is your favorite. This one is the one I'm using under Linux, and I like it because you can see the command you sent, have a history of that, and also the received ASCIIs are displayed right in this screen here. So right now I'm connected to my TTY, the fourth TTY terminal, and it depends on whether or not you are using a serial adapter card or the onboard serial port, you may have a different serial port listed. And also, if you're using a USB to serial device, it might be under the name, device name of a TTY USB instead. So anyway, so now let's connect to the power supply here. And now we're connected. So the first thing I wanted to do is to see if we can identify the connected device. So we do a start IDN question mark. So these are the standard SCPI commands here. So yep, so we identified it, and the string coming back is a Hewlett-Packard 66312A, and here are the version numbers. So then we can do a couple of different things. For example, we can use this to set the output voltage. So let's say volt, let's do a 10 volt. And you probably can't see anything on the screen yet because I haven't turned on the output yet. So let's do a current of 1 amp. And now we can turn on output. I wanted to watch the screen to see what's going on there. So output, let's do a on. So if I hit enter here, you will see that the output is enabled. Now, of course, we can use this to do some measurement. We can say measure voltage, question mark, and it will return the measured output. So it's slightly different than what you set it at because this is the actual measured results. And of course, we can do the same with the current. And basically, it shows you close to 0, the current output. So now you get an idea of how to use a serial to communicate with this HP Agilent 66312A power supply. And of course, I didn't cover, there are a lot of things you can do. You can use this to output a waveform even, to do some programming using the serial command that you can automate your test and record the result at the same time as well. So I hope you enjoyed this teardown and learned something new. If you liked the video, please give it a big thumbs up and remember to subscribe, share, and I will catch up to the next time.